Let's have a look at solid liquid phase behavior and the way it's mapped on a phase diagram. So what I'll use is an illustration that corresponds to what you would have collected in the lab, and this is temperature. And this is composition. So like any binary phase diagram, that's what this is, a binary phase diagram. I have two solids, if you think back to your experiment, that were loaded into a test tube, brought to a high temperature so that they would be in the single phase melt, and then cooled. And the data is then presented on a phase diagram. But I think before we actually look at illustrating it on the phase diagram, I'm wondering maybe if we could just slide this over and remember what the cooling curves looked like. Now the cooling curves are, let's see if I can draw this without being in your way. Small t for time, which is quite rare in this course to have time, and big T for temperature. So I'm just looking at this little black graph, never mind the green box for now. And at time 0, we put our test tube in the hot water bath, and we are up high above the melting point of either pure component, And we cool down over time, so this is going to necessarily need a slope. It doesn't cool in an instant of 1 second, it cools over time. We do our best to keep that cooling rate constant, but it'll most likely have a bit of a curve to it. And then we notice some sort of inconsistency perhaps, and maybe it even supercooled, and then something, even though we were cooling, it began to heat a wee bit, but did perhaps level and then keep going and then do something else and change the slope again. They're not super pronounced, and I think that is typical of what you would have found. If you want textbook definitions, I mean illustrated definitions of these, you can look in textbooks where they have, beautiful slope and plateaus. It doesn't really look like that when you do it in the lab. I think it looks more like this. So we have a couple of things going on here. We are cooling the liquid, and what happened here most likely is that you had a degree of supercooling experienced. Once it did, so it probably went below its normal freezing point, and then for the solution, and then once it started to crystallize, it's an exothermic event, and it kind of brought itself back up to the TM that it should have froze out at to begin with. And so what you see at this point is in your test tube, you probably saw you had your melt liquid, and then you had maybe some crystals growing on the lower free energy surfaces like the air-liquid interface or meniscus and the sides of the glass. And so you have that within a slush, and then with continued cooling you hit what's called the eutectic temperature, and at that point everything solidified, and it just went solid on you at that point in time. Okay, so you have not this supercool, that little bracket there would be your degree of supercooling, but this temperature and this temperature are the two that you would have taken to the phase diagram. So this is a cooling curve for a particular mixture concentration or mixture mole fraction, and you have two temperatures to plot. So you did that a number of times. I'm just wondering, I found this graphic online. It's really, really good. And I'm wondering if I take the camera and just show it to you. I'm going to regret doing this. But let me just see. Oh, hold on. Here we go. So, let me do this. I have to keep the camera minimized as well so I can know you're picking it up. I'll try and hold it still. Maybe you want to freeze frame it for a second. Okay. Yeah, this is neat, right? What you've got here, the numbers across the top, 100, 80, 60, 50, 40, and so on, and then 0 to 100. That's your mole percent instead of mole fraction. Okay. Those are the different cooling curves. So all the lines going down are cooling curves, and the 80-20 is kind of like the cooling curve that I just illustrated. And for every cooling curve except the two pure, M and N, they have two melting points. The first one is super, super subtle, and it's probably masked by their superposition of the phase diagram. But isn't it neat how they took each cooling curve with time, temperature time map, and just X shifted it a bit, and so that they're all on one box, and then they sketch that dashed line through the melting point of the pure and then its depressed melting point because the second component has been added until the eutectic. And see how the eutectic melting is in fact, well, now you know why it's called an invariant. See how it is in fact invariant with, does not vary with composition. It's very cool. And so they kind of superimpose the phase diagram on top of that. So, okay, so now I'm going to go back and we'll sketch our phase diagram. Okay, that wasn't too hard. So let's sketch our phase diagram based on the results that you collected in the lab. And it's just approximating. I don't have the results in front of me, and I'm thinking that your eutectic was somewhere around 37 degrees Celsius and somewhere around 0.5. And I think you had a high one on that side and a low one, so something like that. Okay, let's label the phases. So how many phases are present here? Well, this is at the high enough temperature where everything is in the melt. So this is one phase, and in fact it's the liquid melt. And at any point inside this region here, defined by this piece of pie, any region, so let's take any point in here. If I made a point right there, and I wanted to know what phases are present, I would just do a tie line here this way and a tie line that way, and that shows me that I've got pure solid B, because A is 0, pure solid B in equilibrium with a liquid, and the liquid's composition is defined by this mark. I think what I want to do here is not to look like I'm making more equilibrium lines, so I'm going to make very thick the phase diagram equilibrium lines themselves, so that I can sketch other lines on here, which should have been dashed lines, just to talk about points. So this point, for example, right here, at this temperature, in that overall composition of what's in the test tube, I have in the test tube some solid B in equilibrium with a slush liquid with a liquid, sorry, altogether it's a slush. So I have solid in the end liquid, and the liquid composition is this. So that's the overall composition of what's in the test tube as slush. So it would look, okay, slush, so there's some solid pieces in a liquid. The solid pieces are pure B, and the liquid is this composition. Got it? Let's take a point over here. What is in the tube? Well, the tube is at this temperature. The overall composition in the tube is marked by this mole fraction. Specifically, I have two phases in equilibrium with each other in this test tube. I have solid bits of pure A in equilibrium with a liquid, and the liquid is rich in A but also has some B. Okay, so labeling these, this is one phase, the liquid melt. This is the areas in here, and these two pies are two-phase regions, two-phase, and the phase is, in this case, B plus liquid, and this is A plus liquid. And here at the eutectic, I have A plus B, two phases, A plus B solid. So this is, let's define. This is B solid plus the liquid AB, and this is A, it's not enough room to write it in there, so inside here is A solid, pure A solid, and liquid AB. Inside here, B solid plus liquid AB. And this is one phase. It's liquid AB, of course, but it is one phase. Okay. And this is my eutectic temperature, and that's my eutectic composition. Eutectic composition, and this my eutectic temperature. Yeah. So, have not left much room for navigating through, so let's maybe draw another one again. And this is temperature, this is mole fraction. This is the Tm of A, and this would be the melting point of B, because mole fraction of A is 0 there. Again, I've got one phase liquid AB. Here I have solid B and liquid A plus B. This is solid A and liquid A plus B, and this is solid A plus B. The number of phases here is 2, 2, 2, and 1. So I still haven't left enough room, but we're going to do it. We're going to push our way through. Okay, so cooling curve. The cooling curves that you collected can be represented as vertical lines on this diagram, right there. So let's do this. Let me move that over. So that line right there could look like T versus time cooling curve. We start up here, we cool, there's the pure guy coming out, no supercooling this time, getting better at it, maybe a slight different slope, and then again. So I see 2 points there. So there's my 2 points melting, 1 and 2, and that would correspond to this and this one here. Got it? Okay. So as I'm cooling this, the temperature is just dropping, but then all of a sudden it starts to freeze. Oh, all of a sudden, what's freezing exactly? Tie line. Brings me right to the solid, pure. Right, pure B is freezing out. So crystals of pure B is freezing out. And in fact, this is the melting point depression of pure B, because B usually melts up here, but because you have A in it, it's now melting down here. Right? When you make something in organic chemistry or in the lab and you want to know if you have the right stuff, you do a melting point. The melting point's really low. Right, it's not pure. Okay, so your melting point is depressed. So again, we're going to start over. I'm up here and I start cooling, and there I see crystallization in the test tube. But what is it? Tie line. It's pure B freezing out of solution. It's freezing out of solution, so that as I cool more, yeah, it's, well, you could slide down this, but we'll just look at this. So as I cool, what's it leaving behind? Well, it's leaving behind the tie line. I can't go anywhere with this tie line. It leaves me, I'm right here. Well, that's exactly what it's in equilibrium with. I have pure B and my liquid AB. So then let's say I stop here. Now what? I still have pure B crystals, but more B has crystallized out, and it's leaving behind now a liquid that is, instead of this composition, it's now this composition, until I finally reach this point, and this point is where I see the second crystallization occurring, and that's of the eutectic. Now watch what happens with my tie lines at the eutectic. A tie line here brings me right to this border and right to this border.